Hi everyone, this is Kenny Lee, and let's talk a little bit about the energy of a photon. A photon is a wave packet. It's where Einstein settled the argument between the two fractions about whether light was really a wave or a particle. And he said light was basically both, a wave and a particle, and we called it a photon, which we roughly call a wave packet, where from a certain point of view it looks like a particle and another point of view looks like a wave. We're going to use the idea that light is a wave to kind of represent this. And when we talk about light, we mean any of the electromagnetic spectrum, all the way from radio waves to gamma rays. Okay? So anything in that we simply call light. Light was the first one we noticed because that's what we see. We discovered the others, a couple hundred years ago or so. We've got this basic equation where E for energy, and H is Planck's constant, and it comes in two different flavors, Joule seconds or electron-volt seconds, depending on which one the problem asks for is which one you use, but it's always one of these two constants, and frequency. Now, along with that, since we're talking about light, in light as a wave, we also have where the speed of light, c, is equal to wavelength times frequency. So just like those regular wave problems. And the speed of light is 3 times 10 to the 8th meters per second. So we can combine these and use these equations to figure out the energy of a photon, or if we know the energy, to figure out the frequency or the wavelength of that photon. And that's what we're going to look at next. But it's always going to be one of these two versions of Planck's constant. Depending on if I want the energy in joules, I'll use this one. If I want the energy in electron volts, I'll use this one. All right, let's start off with this one. Let's say we've got a photon of orange light that has a frequency of 5 times 10 to the 14th hertz. And so it means it vibrates up and down that many times every second. And we want to know the energy of the photon in both joules and electron volts. So we'll do both of them. Since I know the frequency, I already know that E equals HF. And so that's the equation I'm going to use. I'm going to first do it in, let's say, joules. So we'll start off with that one. So we still got the same equation, E equals HF. But since I'm going to figure it out in joules, I need to use the joules version of Planck's constant, which is 6.63 times 10 to the minus 34. And I just have to multiply by the frequency, 5 times 10 to the 14th hertz. Okay, this one where you got to remember how to use your scientific notation on your calculator. So 6.63 times 10 to the negative 34 times 5 times 10 to the 14th. I get an energy of 3.315. I could probably just round that up to 2 times 10 to the minus 19 joules. So that's the energy of the photon in joules. So it's a really small amount of energy. What if we do the same thing except this time in electron volts? So for electron volts, we've got the same equation, E equals HF. The only thing we do is substitute in the electron volt version of Planck's constant, 4.14 times 10 to the minus 15 times the frequency, 5 times 10 to the 14th. So again, if we calculate that, 4.14 times 10 to the negative 15, 0.14 times 10 to the negative 15 times 5 times 10 to the 14th, we get something more in the order of 2.07 electron volts. Both these are the same energy, they're just in different measurements. Like this would be like kilometers, and this would be more like centimeters or something like that. And so it's just a different scale. So they're both representing energy, but the electron volt version is more on a proper scale with the amount of energy that's given off. That just is like really small, but this one is much easier to comprehend into rights if we had to write it down. But they're both equivalent to each other. So that's the energy of orange light in either joules or electron volts. All right, let's look at this question here, where I've got the wavelength of the X-ray. Now remember, this energy of a photon works for any version of our electromagnetic spectrum, okay? Not just visible light, but all of them. And sometimes you're given the wavelength, like this one, 6 times 10 negative 10 meters, or it could be given in nanometers. So 0.6 nanometers is 0.6 times 10 to the minus 9. And if I move it over to more proper notation, we move that decimal point over one more and becomes 6 times 10 to the minus 10 per meters if we move that on over. Those are equivalent to each other. You just have to see how it's written in the problem. So I want the energy in joules. And that's a common question, is like, which version of Planck's constant do I use? Well, it depends on what unit of energy you want to find the energy in it. If it's in joules, you use the joules version of Planck's constant. If I wanted it in electron volts, you use the electron volt version of Planck's constant. So let's do this quickly. E equals HF. I want it in joules, so I'm going to use 6.63 times 10 to the minus 34. And I use frequency, but I have the wavelength. I don't have frequency. So that means I need to do one more thing. I need to go back and actually figure out the frequency of this X-ray. Well, any electromagnetic wave travels at the speed of light. So we know that's 3 times 10 to the 8th. Wavelength, 6 times 10 to the minus 10. And we can find frequency. So 3 times 10 to the 8th divided by 6 times 10 to the negative 10. We get a frequency of 5 times 10 to the 17th hertz. Okay, now we know the frequency. So now we can do this. So let's put that in. So there's our frequency. So we got to add it in. 6.63 times 10 to minus 34. Now we know the frequency is that number. 5 times 10 to the 17th. And we get an energy of 6.63 times 10 to negative 34 times 5 times 10 to the 17th. Gives me an energy of 3.315 times 10 to the negative 16 joules. Now, since we know the frequency, we can also figure out the energy in electron volts. We would just have to do this calculation over again, except replacing that with the electron volt version of Planck's constant. Let's do one more example. This time I've got some ultraviolet light that has an energy of 4 electron volts. And I want to know the wavelength of that ultraviolet light. Well, since I know the energy, I want to start off with that. Energy equals HF. Okay, and I've got my energy in electron volts. So I'll use the electron volt version of Planck's constant. So it's 4.14 times 10 to the minus 15. We can figure out the frequency. So 4 divided by 4.14 times 10 to the negative 15. And I get a frequency of 9.66 times 10 to the 14th power, and that will be in hertz. Well, now that I know the frequency, I can figure out the wavelength because we can use the speed of light, where we got 3 times 10 to the 8th equals the wavelength, which we don't know, but we do know the frequency is 9.66 times 10 to the 14th. Do a little division. 3 times 10 to the 8th divided by 9.66 times 10 to the 14th. And we get a wavelength of 3.11, let's call it, times 10 to the minus 7th meters. That's our tutorial about how to do energy of a photon problems. Tune in again. We'll talk about other things about light. Thank you and good night.